In the previous lecture, we discussed about the process of analog to digital conversion, or A to D conversion, and that involves three steps. The first step is sampling, and then quantization, and then encoding. So the A to D conversion process involves these three steps. And we then discussed the process of sampling in more detail, and we saw what happens or how the process of sampling is done. And as a result of sampling, a continuous signal, a signal which is continuous in time, gets converted to being discrete in time. So the process of sampling converts a continuous signal to a discrete signal. And then we also looked at the Nyquist sampling theorem, which governs the process of sampling, wherein it imposes the rule that the sampling rate should be at least twice the bandwidth of the signal, or at least twice the maximum frequency of the signal, which turns out to be equal to twice the bandwidth of the signal. Or equivalently, in terms of the sampling period, we can represent that same condition as Ts, the sampling period, to be to not exceed 1 by 2W. This threshold of 2W or 2F max is called as the Nyquist rate. So when the sampling rate is exactly equal to 2F max, that is said to be sampled at exactly the Nyquist rate. So whenever we say Nyquist rate, it means exactly equal to twice the maximum frequency present in the signal, or twice the bandwidth of the signal. So that is what is called as the Nyquist rate, and we discussed that as well in the last lecture. And then we also discussed about the situation when this condition imposed by the Nyquist sampling theorem is violated. So if we sample a signal at a rate less than the Nyquist rate, then what happens? We saw that aliasing happens, and we discussed about the process of aliasing as the situation where during the reconstruction process of the signal from its samples, some higher frequency components will get translated onto some other lower frequency components. So we gave this very general idea about the process of aliasing, which occurs when the Nyquist criteria is not satisfied, when we sample at a rate, at a sampling rate which is below the Nyquist rate, right? And in the previous lecture, we restricted our discussion in more simple terms using graphical representations and so on. But in today's lecture, we are going to discuss the process of sampling more analytically, and then see what is the mathematics behind it, and how it can be represented analytically, the entire process of sampling itself. So let's move into that process. So here we have on this slide, on the top, which is the time domain continuous signal, which we are going to sample, which is shown in this as this red waveform. So that's our x of t, our original time domain continuous signal, which we want to sample. So let me write down that. So that's our continuous signal. And that is a signal that we want to sample. Now, the second signal which we have here is called as the sampling function, using which we are going to implement or produce the effect of sampling. So the sampling function is nothing but an impulse train. So we can write the sampling function s delta of t as an impulse train, which is delta of t minus nts for n equals minus infinity to infinity. So that's our sampling function s delta of t, where the amplitude of each of these impulses is 1, and the time separation between the impulses is equal to the sampling period Ts, which is equal to 1 upon Fs. So that's our sampling function. And by using the sampling function, we can produce the effect of sampling by simply multiplying our continuous signal x of t with the sampling function s delta of t, and that would give us our sampled signal xs of t. So if we see now, because the amplitude of the impulses in the sampling function are equal to 1 at the sampling instance, that is at 0, at ts, at 2ts, at 3ts, and so on, and similarly at minus ts, minus 2ts, minus 3ts, and so on. So exactly at these sampling instance, the value of the sampling function is 1. At all other time instance, the value of the sampling function is 0. So when we multiply these two signals, that is equivalent to multiplying the amplitude of the signal at the time instant with 1. So whatever is the value here, that gets multiplied by 1, so we get the sample value that is present there. And for all other values in between, the signal value gets multiplied with zeros, so it results in an output of 0. So what we have is effectively the sample signal obtained by multiplying the actual continuous signal with the sampling function, which is nothing but an impulse train. That is a train of impulse functions, or train of delta functions. So we can now write the sample function xs of t. So that's our sampled signal, which is our discrete signal, by the way. And we have obtained that by multiplying the continuous signal x of t and the sampling function s delta of t. So we can write that as x s of t to be equal to x of t multiplied with s delta of t, which is equal to x of t getting multiplied with s delta of t, which is defined as the impulse train, which is delta of t minus nts for n equals minus infinity to infinity, which is simply equal to summation x of nts multiplied by delta of t minus nts. So that becomes our representation or notation for the sample signal in the time domain. So we are looking at this process in the time domain, where we have the time domain continuous signal x of t and the time domain impulse train, which we call as the sampling function. And when we multiply these two, we get our sample signal, which we denote as x subscript s of t. So that gives us our sample function. So analytically, we can represent the sample signal as the product of the actual signal and the sampling function. So again, n ranges here from minus infinity to plus infinity. Now, having seen the analytical representation of the sampling process in the time domain, how do we translate this to the frequency domain and see the analytical representation of the sampling process in the frequency domain? To understand that, we'll use some very basic fundamental principles of the frequency domain and some knowledge, our prior knowledge of the translation from time domain to frequency domain. So for example, if we have the signal x of t, and if we take the Fourier transform of this signal and convert and get its spectrum, we will represent that spectrum, say for example, by x of f. So that's the frequency domain representation of that signal x of t. We will have it as x of f. So we obtain it by computing its Fourier transform. And similarly, the sampling function S delta of t, its Fourier transform will give us its spectrum. So the Fourier transform of the sampling function would give us the spectrum of the sampling function, which we would denote as capital S delta of f, and correspondingly the spectrum of the sample signal, again if we take the Fourier transform of the sample signal, that should give us the spectrum of the sample signal, which we would denote as x sub s of f. Now, rather than taking their Fourier transforms or obtaining the spectrum of the sample signal by taking the Fourier transform of the sample signal itself, we could proceed by obtaining the spectrum of the sample signal using the spectra of the original signal and the sampling function. And to do that, what we do is we will use the property of the Fourier transform, which says that multiplication in the time domain corresponds to convolution in the frequency domain. So here in the time domain, we are multiplying the signal x of t with the sampling function as delta of t. In the frequency domain, that would correspond to convolving their respective spectra. So that means in the frequency domain, if we convolve x of f with s delta of f, that should give us the spectrum of the sample signal xs of f. So we will use this idea to represent the process of sampling analytically in the frequency domain without going into the actual Fourier transformation of the signals x of t and s delta of t and so on. So let's look at that process in the frequency domain now. So now if we denote and represent our original signal spectrum as x of f, and we plot the spectrum here, and if you notice, we are using this triangular shape to represent the spectrum, and that is a very a general procedure in representing a spectrum, because typically most signals have the magnitudes of lower frequencies to be higher, and as the frequency goes up, the magnitude tends to become smaller and smaller and smaller. So the magnitudes of the higher frequency components are usually weaker than the magnitudes of the lower frequency components, and hence the general representation of spectrum for a baseband signal is represented in this triangular form. Again, it could be some other shape as well, but in general, for most practical signals, it is noticed that lower frequency components have higher magnitude, and as the frequency increases, the magnitude of the higher frequency components gets lower and lower. So we denote this as a triangular shape, right? So we have this which is the spectrum of our continuous signal, which has the highest frequency component of f max. And then we have here the spectrum of the sampling function, which is the sampling function is an impulse train, and the spectrum of an impulse train is also an impulse train, but in the frequency domain. So since we had the sampling function denoted as summation of delta of t minus nts, its spectrum would be also an impulse train, but in the frequency domain as delta of f minus nfs. So s delta of f would be, I'll just write it here. So s delta of f is nothing but that's equal to summation delta of f minus n fs, and for n equals minus infinity to infinity. But now when we take this spectrum, it has a scaling factor of 1 by ts, or simply fs. So that's a scaling factor we get with the spectrum in the spectrum of the of the sampling function. So we've denoted that here. So the amplitude of each of these pulses in the frequency domain that you see is Fs equals 1 upon Ts. So that's the spectrum of the sampling function, S delta of F. Now in the frequency domain, the equivalent process of multiplying the time domain signals is convolution. So multiplying x of t and s delta of t corresponds to convolving x of f and s delta of f. So the process that's going to happen here between these two spectra is convolution. So convolving these two will produce our spectrum of the sample signal, which we denote as xs of f. So the spectrum of the sample signal, so let's write here, xs of f is nothing but the convolution of the spectrum of the original signal x of f with the spectrum of the sampling function s delta of f. And by the way, the sampling operation or the convolution operation is denoted by the star inside the circle. So I'm using the star inside the circle to denote the convolution operation. So the spectrum of the sample signal is obtained by convolving the spectrum of the original signal with the spectrum of the sampling function, so which is equal to x of f convolved with summation, right, I'll use that, fs summation delta of f minus n times fs, where n goes from minus infinity to plus infinity. So that is the analytical representation of the sample signals spectrum, and we could simplify that as simply fs into summation of x of f minus n fs, where n goes from minus infinity to plus infinity. Now if you notice here, when n equal to 0, you will get x of f scaled by fs. So again, one thing I need to write here is that this should be fs, which is 1 by ts. So when n equal to 0, we simply get this term as x of f, which is this term. When n equal to 1, it is x of f minus 1 fs. That means it is a shifted version of x of f by 1 fs. So that is that term. Again, it is going to have a magnitude of 1 by ts, which is fs. And when n is equal to 2, it is x of f minus 2 fs, which is this term here, this representation here, this replica. And similarly, when n is equal to minus 1, it will be x of f minus fs, so x of f plus fs, which is a left shifted version here. So we have this term when n equal to minus 1, and similarly when n equal to minus 2, we have this term, and so on. So n ranges from minus infinity to plus infinity, and I've just depicted here for n equal to minus 2, minus 1, 0, 1, and 2. So what we see is that the spectrum of the sample signal contains basically the spectrum of the original signal and replicas of it at integer multiples of the sampling frequency, but obviously they are scaled by the scaling factor, which is 1 by ts. Now again, what I have depicted here corresponds to the case where the sampling rate fs is greater than 2f max. So this part here is f max, and that is minus f max. So that distance is also f max, that distance is also f max. So here fs is greater than 2f max. So what I have drawn here are The analysis that are made here is for the condition that the sampling rate fs is greater than twice fmax, or it is greater than the Nyquist rate. So we see in the analytically now that the process of sampling indeed produces a spectrum where the spectrum of the sample signal contains replicas of the original continuous signal spectrum at integer multiples of the sampling frequency, right? So that's our representation, or the analytical representation of the sampling process. Now, while we are at this, we can easily see that the process of reconstructing the original signal from the samples can be thought of as getting back our original signal spectrum from the spectrum of the sample signal. So if you look at the process of reconstruction in the frequency domain, it becomes more intuitive as to how this can be done. So that's the spectrum of the sample signal, and that's the spectrum of, and we want to reconstruct our original signal from the sample signal, and that can be achieved by simply low-pass filtering the sample signal. So when we do low-pass filtering, or when you apply low-pass filtering to the sample signal, that would mean that only this part of the spectrum of this replica centered on 0 would get extracted, and all the others would get discarded. So we would get back that part of the spectrum which corresponds to the spectrum of the original signal. So the process of reconstruction of the original signal from the sample signal can be achieved by a simple low-pass filter. So low-pass filtering the sample signal would give back our original signal. Of course, it would be scaled by a certain factor, and we can always amplify it and get it back to the original level. But it is very intuitive to see from this diagram that the reconstruction process can be done using a low-pass filter. Previously, we had discussed about the analytical depiction of the sampling process, where we saw that the sampling process can be affected by multiplying the continuous signal, or the signal which is continuous in time, with what we call as a sampling function, which is nothing but an impulse train, where the deltas are separated by a duration of the sampling period. And by multiplying these two signals, that is the original continuous signal and the impulse train, that is the sampling function, we get our sample signal. So that's the time domain representation of the sampling process. And therefore, analytically, we can now write the expression for the sample signal as the product of the actual signal, the continuous signal, and the sampling function. Now, in the frequency domain, that corresponded to the convolution of the respective spectra of the original signal and the impulse train. So in the frequency domain, we had the spectrum of the original signal, which had a maximum frequency of fmax, and the spectrum of the sampling function, which is the impulse train, and the spectrum of the impulse train is another impulse train, but the difference now is that the separation between the impulses, or the deltas, is fs rather than ts, and there is a scaling factor in the amplitude of these, or the heights of these deltas. And multiplication in the time domain corresponds to the convolution in the frequency domain from the properties of the Fourier transform. So multiplying the signal with the impulse train in the time domain corresponds to convolving the spectrum of the signal and the spectrum of the sampling function. So when we convolve this, we get the spectrum of the sample signal, which we see here, and the figure that we see here, or the spectrum of the sample signal that has been shown here, corresponds to the case where the sampling frequency fs is greater than the Nyquist rate 2f max, right? So we have the sampling rate which has been chosen to be greater than 2f max. So the spectral replicas in the sample signal are having a space between them. So there is a spacing between them because of the condition that the sampling frequency is greater than 2f max. So we have f max, that's another f max, so 2f max, plus this additional spacing term here. So that corresponds to the sampling frequency fs to be greater than 2f max. Now, with this depiction, we can now discuss about the reconstruction process. If you want to reconstruct the original signal from the sample signal, that means we are trying to get back this original spectrum from the spectrum of the sample signal. So we just want to get rid of these extra replicas and retain only the central term which is centered on 0. So that would give back our original signal, and that could be achieved very easily by low pass filtering. So if we pass the sample signal through a low pass filter whose pass band extends till f max, then we have the situation where only the central replica is passed through and all the other replicas are filtered out. So that would give us back our original signal. So the reconstruction process can be implemented very easily by low pass filtering. So if I just draw the frequency response or the magnitude response of a low pass filter, so we say that a simple low pass filtering like this would, let me make it a bit clearer. So we make it like this. Oh. Okay, so a simple low pass filter whose pass band is extending from, say, minus f max to plus f max. So let me be more precise. So let me just restrict it to this. That would give us back our original signal, and all the spectral replicas which are present in the sample signal would get filtered off, resulting in only the spectrum that we desire, which is for the original signal, the continuous waveform. Obviously, there is a scaling factor here, and that could be overcome or removed by amplifying after the filtering process. Now, the frequency response of the filter that is shown in blue here is an ideal filter, and in practice we cannot implement an ideal filter because the impulse response of an ideal filter is non-causal, so therefore it cannot be implemented in practice. So practical filters are going to have a gradual roll-off from the pass band to the stop band. You're not going to have a flat transition band. Rather, you're going to have a gradual transition band where the roll-off occurs from the pass band to the stop band in a gradual way. So an actual practical filter would have a frequency response which is something like this. So that would be the frequency response of a practical filter that could be used to reconstruct the original signal from the sample signal. Now in this case, since we have the sampling frequency to be greater than the Nyquist rate, even a practical filter would be able to recover the original signal, and there is no problem with this. So the reconstruction process is simple by using a low pass filter. Now if we look at the spectrum of the sample signal when we have the sampling rate to be exactly equal to the Nyquist rate, so let's have a look at that. Here I have depicted the scenario where the sampling rate fs is exactly equal to the Nyquist rate. So here it's fs is equal to 2f max. So when the sampling rate is exactly equal to the Nyquist rate, then we have the spectral replicas centered at fs, 2fs, 3fs, and so on, And because fs is exactly equal to twice the maximum frequency, so that is f max, and that's another f max, so we have fs is equal to 2f max. So now we see that the spectral replicas are touching each other. So you see there is no gap between the spectral replicas in the sample signal, so they are just touching each other. So that is what we see when we have the when you've done the sampling at a rate which is exactly equal to the Nyquist rate. Let me mark these points. So that's minus 2fs and minus 3fs and so on, right? So you'll have it like this. Now, in order to reconstruct and get back our original signal from the sample signal, again, like before, we could use a low-pass filter. So if we use an ideal filter like this, we could get back our original signal spectrum. But in practice, however, it is not possible to have an ideal filter, but rather what we would have is a practical filter which has a gradual roll-off from the stop band to the pass band. So it would be something like this. And due to this gradual roll-off, what you see is that even for the case where fs equal to 2f max, which satisfies the Nyquist sampling theorem, because the Nyquist sampling theorem states that the sampling rate should be greater than or equal to 2f max, which is satisfied here in the theoretical sense. But in practice, however, the reconstruction would become difficult, because with a practical filter shown by the red frequency response of the low-pass filter, it would get back the original spectrum, but it would also give us back some extra higher frequency components which were not there in the original signal because of the gradual roll-off in the magnitude response of the low-pass filter, right? So hence, in practice, we use sampling at a rate which is greater than the Nyquist rate, so that there is some spacing between the spectral replicas, and that would allow us to use a practical filter to recover or reconstruct our original signal without introducing any undesired frequencies or frequencies which were not present in the original signal. So in practice, okay, so let me write here, in practice, fs greater than 2f max is used. Why? Because it simplifies the reconstruction process using practical low-pass filter. LPF stands for low-pass filter. So by having some spacing between the spectral replicas, which can be achieved by choosing the sampling rate to be greater than the Nyquist rate, the reconstruction process can be implemented using practical low-pass filters. Now let's look at the third case where the Nyquist criteria is not satisfied and sampling is done at a rate less than the Nyquist rate. So in this case, we have fs is less than 2f max, and in this particular case, I have chosen fs to be precisely 1.2 f max. So what I marked here is, so for example, if that is f max and that is 2f max, so I marked fs at 1.5 f max. So precisely I have marked this diagram as selecting fs to be equal to 1.5 f max, which is less than the Nyquist rate, which is less than 2f max. So in this scenario, what we see is that the spectral replicas, again, because of sampling, are going to have periodicity at integer multiples of the sampling frequency. So we are going to see the first replica at 0, the second one at fs, which is equal to 1.5 f max, the second one at 2fs, 3fs, 4fs, and so on. So that would be minus fs, minus 2fs, that's minus 3fs, and that's minus 4fs. So what we see here at the bottom of the screen is the spectrum of the sample signal, which has been sampled at a rate below the Nyquist rate. Okay, in this particular case, precisely at 1.5 fmax rather than the minimum value of 2 fmax. Now, in this case, if you see that not only can a practical filter not recover the original spectrum, but even an ideal filter would not be able to do it without distortion. So even if we used an ideal filter, so if you see there was a filter which was ideal, still what we see is that there would be the recovery of the original part of the signal, but there is some frequency components which come under this triangle, the second triangle, the neighboring triangle. So if you see these parts, these are high frequency components which have translated onto low frequency components, and because they lie within the filter's passband, they would come into the reconstructed signal, so which is what we call as the aliased components. So this overlaps that we see here, those would cause aliasing. So those are the aliased components of the signal. So that represents aliasing. And even with an ideal filter, it will not be possible to reconstruct the original signal without distortion. And with a practical filter, the problem would even get worse. So because a practical filter may have a gradual transition band, that means it is going to allow even more additional frequencies to come in. So there would be some extra frequencies from this part also that would appear in the reconstructed signal. So hence the sampling done at below the Nyquist rate is definitely a no-no, because it is going to cause aliasing. So we see here aliasing occurring, and even though theoretically fs equal to 2 fmax is a sufficient condition, in practice, however, it would make the reconstruction process more complex, because it would require highly selective filters which become more and more complex. In fact, it requires ideal filter that is practically not implementable. So therefore, it is desired that the spectral replicas have spacings between them, and that would be achieved only by having fs greater than 2 fmax, not equal to 2 fmax. With equal to 2 fmax, there would be no spacing between these spectral replicas. So to have spacing between them, we need to choose fs greater than 2 fmax. So we will have some spacing between the spectral replicas, and that would allow us to use practical filters to filter out the desired band, which is centered on 0, to reconstruct our original signal. So that's the case for fs equal to 2 fmax. And then, as you see here, when the sampling rate is below the Nyquist rate, obviously there is going to be aliasing, and with aliasing we are going to have some high frequency components getting translated as low frequency components and appearing in the reconstructed signal. So with aliasing we have high frequency, or not all of them, some high frequency components get translated to lower frequencies. Okay, and that is the problem of aliasing, which occurs when the Nyquist criteria has not been satisfied. In the next part of the video, I am going to illustrate and show how to calculate the alias frequencies, right? So in general, the aliasing means some high frequency component getting translated to a lower frequency, but how do we work out which high frequency components get translated and to which lower frequency components they get mapped to? So we'll look at that process in the next part of the video. Now, What we're going to do next is to look at aliasing in more detail and to figure out how to compute the alias frequencies given the sampling rate and the input frequencies that go into that particular sampler. So let's have a look into that. So to understand this, let us consider that we have a sampler or a sampling system whose sampling rate is fixed to be some fs. So that is not in our control now. The sampling rate of that circuit or of that system has been fixed, so that cannot be altered. Now if we have such a sampler and we are using the sampler to convert a continuous signal to a discrete signal, then what is the maximum input frequency that can be applied to this sampler such that there is no aliasing occurring when we have a reconstruction of the original signal from this discrete signal? So what is the maximum input signal frequency that can be applied here in order to in such a way that there is no aliasing? So to look at that, we just need to rewrite this equation or condition from the Nyquist sampling theorem in a different way. So we can write this as f max should not exceed the sampling rate by 2, or 1/2 of the sampling rate. So given that the sampling rate is now not in our control and we have like a black box system whose sampling rate is fixed, that means if we don't want aliasing, we need to ensure that no frequency above fs by 2 enters the system. If it enters, if any frequency greater than half the sampling rate enters the system, then there will be aliasing. So the maximum frequency that can be applied to this sampling circuit whose sampling rate is fixed to fs is half the sampling rate. So fs by 2 is the maximum frequency that can be applied without causing aliasing when we have the sampling rate fixed at a certain value. Now we'll now see with an example how to compute the alias frequency given a sampling rate and a range of input frequencies. So suppose that we have a system whose sampling rate is fixed to some fs. That means the maximum frequency that can be applied as input to this system is half the sampling rate. So that would be our f max. So f max is half the sampling rate, so fs by 2. So any frequency above half the sampling rate would suffer aliasing. And to understand this better, let me assign some values to these parameters. So let's say our system has a sampling rate of 100 samples per second. So in that case, or 100 hertz, but a better way to represent or a better unit for the sampling rate is samples per second. In that case, the maximum frequency that can be applied to such a sampler whose sampling rate is 100 samples per second would be fs by 2, which is 50 hertz. So any frequency above 50 hertz would cause aliasing. Now let's say we apply a frequency, say, of 10 hertz, and since 10 hertz requires a sampling rate of 20 samples per second and we have a sampling rate of 100, there would be no problem. So 10 hertz would reconstruct back as 10 hertz, so there would be no issue. And similarly 20, 30, 40, up to 50 we're not going to have a problem, because up to 50 the condition is satisfied. If the input signal is 50 hertz, then the sampling rate should be at least 2 times 50, which is 100, and we have 100 samples per second. So theoretically there should be no problem. So up to 50 hertz we will have no problem. So what I'm writing here is the original signal frequency, and this is what we call as the aliased frequency. So I'm going to write the original frequency and the aliased frequency, and up to 50 hertz we are not going to have any problem. So if I mark these points here, so that's 10, 20, say 30, 40 and 50. Okay, now if we give a signal of 60 hertz as input to this sampling system whose sampling rate is 100 samples per second. What would be the reconstructed frequency of this signal? Would it be aliased or not? So let me be more precise here. Up to 50 Hertz, there's not going to be any aliasing, but beyond 50 Hertz, there's going to be aliasing. So I'm going to rewrite it here. So original and aliased. Okay, so up to 50 there is no problem. If we go above 50, that is say even 51 or 52, it is going to cause problems. But let's say we choose a value of 60. What happens to the 60 Hertz? The 60 Hertz is going to come back as 40 Hertz. It would get mapped to a lower frequency of 40 Hertz. How do we know that? Now, if from this illustration that I'm showing you here, the red line forms like a wall here. It's like an upper boundary of the reconstructed signal frequency. So whatever signal that we reconstruct from the discrete signal, the reconstructed signal will have no frequency component above half the sampling rate. So that forms like an upper boundary, and we have 0 Hertz as the lower boundary. So the reconstructed signal would be bounded between 0 and half the sampling rate. So up to 50 Hertz, there would be no problem. So if we are going up to 50 Hertz, there is no issue at all. But 60 Hertz means it cannot go any further. It cannot go any further beyond this boundary because it's like a wall. So it has to turn back and cover an extra 10 Hertz. So it covers the full 60. So we have from 0 to 50, and then it comes back by 10. So it has now covered 60 or 60 units. So when it comes to 60, it is now corresponding to 40 here. So that's 10, 20, 30, and that's 40, and here we have 50. So 60, it becomes 40. Similarly, if it is 70, so it has to traverse through to 50, come back to 60, and then come to 70, and 70 is nothing but 30. Similarly, 80 means 20, so 80 will become 20, 90 will become 10, and 100 will become 0. It has come here. So it's like being in a room which is bounded by 2 walls, and if you're asked to walk a certain distance, which is more than the width of the room, then to cover the distance, we would go back and forth between the walls to make up the distance. Similarly, when we have a system whose sampling rate has been fixed to a certain value, then the reconstructed frequencies would be bounded between 0 and half the sampling rate. So they would be traversing back and forth between these 2 boundaries of 0 and half the sampling rate, and depending on the value of the input signal, whatever distance it traverses and wherever it reaches while traversing the distance, that would correspond to the aliased frequency. So the original frequency of 60 Hertz gets mapped to 40, 70 gets mapped to 30, and so on, and up to 100. At 100, it is getting mapped to 0. So a signal of 100 Hertz sampled at 100 samples per second gets aliased to 0. Now, if we go beyond 100, so let's say 110, so 50, 100, 110, 110 would map to 10. So I'm going to continue writing here. So 110 will map to 10. Similarly, 120 would map to 20, 130 would map to 30, 140 would map to 40. So let's keep going. 120 would map to 20, 130 would map to 30, 140 would map to 40. So what we have on the left here is the original frequencies, and what we have on the right here are the aliased frequencies. And what we notice is some higher frequency is getting translated onto a lower value, a lower frequency value. So, and we defined aliasing to be the mapping or translation of some higher frequency onto some lower frequency, because the Nyquist criteria has not been satisfied. Because, for example, for a signal of 60 Hertz, the Nyquist criteria says that the minimum sampling rate should be 120. But we are sampling only at 100 rather than 120. So for 60 Hertz and 70 Hertz and 80 Hertz, for all these frequencies above 50, the Nyquist sampling criteria is not satisfied, and therefore all these frequency components get aliased and get translated onto lower frequencies when the reconstruction takes place from the discrete signal back to the continuous signal. So the process of sampling, if it is not done by following the Nyquist sampling theorem, then we'll have aliasing. And we've seen now in a very simple way and an intuitive way how to compute the alias frequency from a given or input frequency. And again, it's not necessary that all input frequencies will be aliased. Only those frequencies whose values are greater than half the sampling rate would get aliased. So for a sampling rate of 100, half the sampling rate is 50. So up to 50, there won't be any problem. If it's 51, so it will go and come back 1 unit, so that will correspond to 49. 52 will become 48, and so on, and 60 becomes 40. So like this, we can go on and on and on. So 50, 100, 150, 200, 250, 300. We can keep traversing this and compute which frequency gets aliased to which lower frequency. So that's the process of computing, or the method of computing the alias frequency from the given values of the input frequency and the sampling frequency. Now, we also have a formula for computing the alias frequency given the value of the input frequency and the sampling rate. And the formula for that is, if we denote the alias frequency as F subscript aliased, we can write that as N times Fs minus F, and we take the magnitude of that, where Fs is the sampling rate, F is the input frequency. So let me write down here, Fs is the sampling rate, F is the input frequency, and N is an integer that makes N times Fs, or the product N Fs, nearest to F. So we need to choose the integer N in such a way that N times Fs is nearest to F. So let's illustrate this by using our previous values, where we had Fs to be 100, and let's say our input frequency is 60, right? So let's choose our input frequency to be 60. So in this case, F aliased would be N times 100, which is NFS, minus 60, and we take the magnitude. Now, what value of N would make NFS would make this component nearest to 60? That would be N. So if we choose N equal to 1, 1 into 100 would be 100. 100 minus 60 becomes 40. If you choose N equal to 2, it will become 200 minus 60. 200 is much farther from 60 than 100. So we need to choose N in such a way that this entire product, N times Fs, becomes nearest to this input frequency F. So we have to choose for this N equal to 1. So here we have to choose N equal to 1. So that would make it 100 minus 60 magnitude. So that is equal to 40. And that is exactly what we saw here. 60 got mapped to 40. Similarly, let's say we choose say 120. So if we have f is equal to 120, then let's see what happens. The alias frequency here in this case would be f aliased is equal to the magnitude of n times fs is still 100 minus 120 magnitude. So what value of n would make this product of n into 100 nearest to 120? Obviously it's going to be 1. 1 into 100 is going to be 100. 100 and 120. So between 100 and 120 the difference is 20. But if we choose n equal to 2, this will become 200. Between 200 and 120 the difference is 80. So we need to choose n such that the difference between them becomes smallest, or those two numbers are nearest to each other. So here again we'll have to choose n equal to 1. So when we choose n equal to 1, so that becomes again 100 minus 120, which will become 20. So it's minus 20, and the magnitude of minus 20 is 20. So if we again see here, 120 has mapped to 20. Let's take one more example where let's say f is equal to let's say 180. So in this case the aliased frequency f aliased will be equal to n times 100, that's nfs, minus 180. So now what value of n would make nfs nearest to 180? If we choose n equal to 1, 1 into 100 is 100 minus 180, the difference is 80. If we choose here the value of n is 2, 2 into 100 is 200 minus 180, the difference would be 20. So 2 would be the the number for n that would make nfs nearest to 180. If we choose 3, 300 minus 180 is 120. So the value of n which makes these two numbers closest to each other is n equal to 2 in this case. So if we choose n equal to 2, that becomes 200 minus 180, and if we take the magnitude again we get 20. Now we can see it from the illustration as well. So what happens to 180? So if we are sampling 180 at 100 samples per second, so it will traverse 50, 100, 150, 160, 170, 180, and you see 180 is mapping onto 20. So 180 is coming to 20, and that is exactly what we got here. 180 is getting mapped onto or getting aliased to 20 hertz. Now another important observation that we have to make here is that there could be multiple higher frequency values that could get mapped onto the same lower frequency values. For example, 120, the original frequency 120 is getting aliased to 20. The original frequency 180 is also getting aliased to 20. So there are multiple frequency components which are getting distorted and getting mapped onto the same lower frequency. Now the original 20 hertz, for example, the 20 hertz signal, if we had an original signal whose value was 20, that would come back as 20, because for 20 hertz the Nyquist criteria is satisfied. So the 20 hertz had no issue, but the 80 hertz has become 20, the 120 has also become 20, the 180 has also become 20. So all these frequencies are coming and getting mapped onto 20, and they would result in the original 20 also being distorted, because these higher frequencies are now coming and sitting in the place and getting mixed up with the original 20 hertz, which had absolutely no problem at all. So aliasing is a big problem. So to avoid that, what we do in practice is that when we have a system where the sampling rate is fixed, we put a filter in front of that sampler, which we call as a band limiting filter or an anti-aliasing filter, where the filter would not allow any frequency greater than fs by 2 to enter the sampling system. So to avoid aliasing, every sampling circuit or system has an anti-aliasing filter in front of it so that it would block off all frequencies greater than half the sampling rate. So that's a practical consideration that we do, wherein we introduce an anti-aliasing filter. So an anti-aliasing filter is used before the sampler to prevent any frequency greater than fs by 2, which is half the sampling rate. So to prevent any frequency greater than fs by 2 to enter the sampling system. So thereby aliasing can be avoided.